speaker, Shubham Nagarkar.
Yeah, that's right.
Okay, great. At USC, and he'll be covering the topic of crisis computing workflows, multimodal social media content for improved emergency response.
Thank you.
Thank you.
So hello, everyone. I hope you're having a great day today. So let me introduce myself. I'm Shubham Nagarkar. I'm a computer science grad student at USC. So I'm currently in my third semester, and I've been working at SciTech Lab since January 2021. So my key areas of interest are mainly computer vision and deep learning. So at SciTech Lab, currently I'm working on a project which is actually a combination of both computer vision and NLP, and we're trying to import it to the Pegasus workflow management system. So today I'll be talking about my work, that is the crisis computing workflow. Basically, it uses social media content for improving the emergency responses. So why is this exactly required? So let's consider any disaster. For example, there are floods, there are forest fires, etc. So during such calamities, what happens is the information is not actually spread to each and everyone all across part of the world, right? So the main source of information here is the social media websites like Twitter. So whenever there's some sort of calamity, like let's say floods, so people are actually tweeting about what is happening at that location specifically. So this information is given out in the form of two types. So let's say there are like people are posting images, people are posting tweets. So from these images and tweets, one can know what is the infrastructural damage which is taking place at that instant, who are the victims, like what has been done to actually help these people, and what is the scale of these events. So if you see that it is very essential that we need to use this information in some way, because it can be really crucial for planning effective and timely responses by the government or the NGOs or the volunteers who really want to help the people in distress and to ease the situation. So in order to do this, we are using a very popular and the only present data set, which is called as the crisis MMD data set. So I'll give a brief overview of this data set. So this data set basically consists of 7 disaster events. The disasters might include hurricane, wildfires, earthquakes, floods, etc. So all these disasters consist 3 types of annotations. The first one is informative or non-informative. So basically it tells us whether this image or this tweet is basically informative or not. Second is the humanitarian categories. So inside humanitarian categories, we have something called as if there's loss of lives, if there's damage of property, loss of like vehicles, etc. And the third category is basically damage severity. So basically it tells us whether the damage is too much or it's mild or there's no damage at all. So in this data set, we actually have an access to 16,000 tweets and we have 18,000 images. So it actually consists of a lot of images, but we have sampled a subset of that data set, which accounts to total 16,000 and 18,000 for text and images respectively. So what are the main challenges in doing this? Firstly, so when there's some sort of disaster, the Twitter is overflooded with random tweets and images. So the main challenge here is to actually find the relevant data, because what we see is most of this data is irrelevant. For example, consider the image on your left. So this image and the tweet itself actually tells us about the certain condition that, let's say here, the hurricane has been hit Houston. So it's really informative image. But if you see the second image here on the right-hand side, you'll see that the tweet says that the couple's wedding has been canceled just because of a flood. So actually, this image is not really important for the government to take any measures, right? So this brings us to the second important challenge, that is filtering the data. By filtering, what I mean is basically to actually classify which tweet or which content is actually informative and not informative. And third important challenge is basically the scarcity of annotated data set. Even though we have like overflood of tweets, only a fraction of it is actually annotated and actually important. So that's why we're only sticking with one data set which is available, that is the crisis MMD. So how do we tackle these challenges? So in order to do so, we have two-step approach. Our first approach and the foremost is our main goal is to improve our performance in the classification task. So we are sticking to only single classification task, that is informative and non-informative on this crisis MMD data set. In order to do so, we have 2 methods. First is the traditional method and second is the novel method. In case of traditional methods, we are using pre-trained networks like ResNet 50 for images, and we are using pre-trained embeddings, that is Globe embeddings, which is basically trained on the internet data, which is crawled from the various websites. And in case of novel methods, we have actually explored newer methods, which is called as contrastive learning for images, and we are using something that's called as attention-based domain-specific embeddings for texts. And our second approach is to further increase and improve the performance of these classification tasks by using something called as multimodal learning. Again, there are 2 methods here, which is called as late fusion and early fusion. So let's go into depths of these methods. So first, multimodal learning. So let's say you have some information from one source. You kind of not trust it exactly, but you're happy with that information. But if you have one more source which actually confirms that information, then you can actually trust that information, right? So this is the same intuition behind using the multimodal learning. So we have two types of modalities. That is, one is image and second is the text data. So the main aim or main goal of doing this is basically to combine the strengths of each individual modality and to cover up for its weaknesses. So we can actually combine both these modalities together in two stages. That's first is the later stage or the early stage. So this brings us to the two methods, that is late fusion and early fusion. So let's consider the late fusion that is on the left-hand side. So you have an image and you have an image pipeline that is a RESTnet model. So you'll supply this image to this model and you'll get some output classification and output probabilities. Similarly, you'll give some tweets to this text pipeline and you'll get some output classification and output probabilities. So now what you do is actually you take these probabilities together, you fuse them with one method or the other, and you get a final classification output. So this is called as late fusion because we are fusing it in the end after the model has given its output. So let's move to early fusion. In case of early fusion, what we are doing is instead of fusing it at the end, we take the intermediate representations of the image and text. So for example, an image is, let's say, of a size 600 cross 600. So that's a huge information. So we want a concise representation of that information. So we reduce that image through convolutions into one single 128 dimension embedding. So that is for image. And similarly, we take the tweets and we reduce it to the 64 dimension embeddings. So now once we have these two embeddings, that is the representations of the image and the text, we fuse them together. And then we give it to some multi-layered perceptron to give us the final classification. So this is how early fusion works. And our last novel method is called the contrastive learning method. So I'll give a basic intuition how this works. So consider you have an original image of a cat. You'll apply two types of transformation. So if you see the upper image, it is basically zoomed and cropped. And if you see the lower image, the contrast of the image is changed. So what you do now is basically you take an encoder, it might be a RESTnet or anything else. So you pass this image to this encoder and you'll get some representation output Zi. Similarly, you'll pass the second image, that is the bottom image, through the same encoder and you'll get some output representation Zj. So the intuition here is, if you see these two images are originated from a single original image of a cat. And you can clearly see that these images are similar. So the intuition is basically the Zi and Zj representation should also be similar. So our main goal is to reduce the loss between Zi and Zj, that is to maximize the similarity. So once this model is trained, we get the intermediate representations, that is Hi and Hj, and we can use it for downstream tasks. In our case, it is basically classifying whether the information or the image is informative or non-informative. The main reason for using contrastive learning is basically, so let's say if two data points belong to the same class, contrastive learning actually puts them close together and forms a cluster. And if the two data points belong to different classes, it basically pushes them away from each other so that we have clear distinction and our classification task becomes simple. So let's move on to the results now. So the first table you see is the results for our traditional methods. So basically here what we are doing is we are comparing our work with an existing work by Gautam, which was published in 2019. So we are using the same models as used by that paper, that is BiLSTM for text and RESTnet for image. So one interesting thing here to note is basically we're using the same architecture, yet we are getting better results as compared to the existing work. The main reason here is because so they've not disclosed their own training methods. So what we are doing differently here is we are trying different methods of augmentation. We are actually using different optimizers. We are using hyperparameter tuning to get best set of parameters. So that's why we're getting better accuracies as compared to them. And we're actually able to beat their baselines very clearly. So let's move on to the second table, which is the early fusion. So now we are comparing our work to another paper, which was published in 2020 by Olfi. So that paper, basically, they're using, again, the BiLSTM and RESTnet pre-trained models to do early fusion. But in our case, we are exploring novel models like supervised contrastive called a SubCon and BERT model. And we can see that with these novel methods, we actually are defeating the baseline by a very high margin and we're getting better results. One more important thing to note here is basically with the help of multiple modalities, that is text plus image, we are getting even better results in the single modalities, that is for text and for image. So this is one of the snippet from the trained SubCon embeddings. So the reason before I told you about the reason why we are using contrastive learning methods, so this is the visualization for it. So you can see that the blue class, that is non-informative class, is very clustered closely together. And it is clearly away from the other class, which is informative class. So now it becomes easy for us to draw a line and basically classify these two classes. So these are the last set of results for late fusion. So in late fusion, again, we are comparing our work with Gotham, and we are clearly beating the existing baselines in three types of late fusion. First one is the mean probability concatenation. This is a very simple method wherein we are just taking the output probabilities of text and image, and we are just taking an average of them. The second is the custom policy. That is nothing but a simple neural network. And the last one is a simple logistic regression model. So with all these three models, we are achieving accuracies as high as 92%. So this is the entire workflow, and this workflow we have been importing to the Pegasus workflow management system. So one important interesting thing to note here is basically we're separating into two workflows. First workflow is called as the late fusion workflow, and second workflow is the early fusion workflow. The reason to do this is because since we are comparing our work with the two different papers, we needed to keep it separate. So you can see three colors here. The one in the light lavender color is basically the tasks which are common to both the workflows. The one in yellow is basically the late fusion workflow, and the one in red is early fusion workflow. So let's zoom into these tasks. So on the left-hand side, you will see it's a text pipeline, and on the right-hand side, you'll see it's an image pipeline. So the input is basically different CSVs for tweets, and for images, it's a directory when all the images are stored. So these blocks basically are the pre-workflow tasks. So by pre-workflow, what I mean is before giving these jobs to Pegasus, these are some computations we need to do before. So that is basically for tweets, what we're doing is we're combining all the CSVs, and then we're splitting them into train, test, and validation. Similarly, for images, we are taking the same split from tweets so that the IDs match together. And then we have similarly train, test, and validation images here. Yeah. So the next is the first job for the Pegasus for both text and tweets. So this is a pre-processing job, basically. So in case of tweets, what we are doing is we're cleaning the tweets by removing stop words, punctuations, and URLs. And in case of images, we are just resizing the images so that each and every image is of the same size, that is 600 cross 600. One more interesting thing to note here is basically these jobs are parallel jobs. So basically, these images are divided into different sections, and these different images are then processed on different computing nodes so that this speeds up the process. So let's move to the core part of the late fusion, which is the training and the inference part. So let's focus on the left-hand side. You will see three jobs. That is perform HPO, the next is train bilastier, and next is run inference. So the HPO is basically what we are doing is we're using a library called as Optuna, and we are finding the best set of hyperparameters for the respective model. So the output of this job is basically a text file, which will give us the best set of hyperparameters. So now the next job, which is the training model job, it uses this best set of parameters, and it gives us the best set of model. So now the next job is basically the run inference, which uses as an input the best trained model, and it basically outputs the probabilities and classes on the test data set. So these three jobs, which are similar to the image pipeline as well. So this brings us to the last job of the late fusion workflow, that is the late fusion itself. So it takes the output CSVs from both these inference on the text and the image models, and it fuses them together, performing the three types of late fusion techniques, which I discussed before. Similarly, in case of early fusion workflow, so the trained subcon model and the trained BERT model are then passed to the generate embeddings job. And in this one, so this job basically outputs a CSV file, which will give us 128 dimensional embeddings corresponding to each image. And it will for the BERT model, it generates 64 dimensional embeddings and converts it into CSV. So now the last job, which is the early fusion, it basically takes both these CSVs together, and it adds a multi-layered perceptron to which these CSVs are given as an input. And finally, we get a classification output. So this is the end of the early fusion job. And so is my presentation. Thank you so much.
All right, thank you very much. Does anybody have any questions?
Yes, I have one.
Please.
So thanks, Shubham, for your great talk first. So I had one question, like the first one is more like ML oriented, I guess. Mm-hmm. So you talk about augmentation and like, you know, you can add like images or text. I mean, you can add text description to images, things like that to, you know, get a better accuracy, a better context. So do you think you can add like any other kind of sources, like an audio record, for example, or some video or some, you know?
Yeah, so that would be actually really great. So the one issue here is we don't have actually a data set which will provide us with different modalities. So right now we have two modalities, that is text and image. But let's say if there are people who are posting videos as well about the disaster which is taking place. So what we can further do is we can have a third modality, that is the videos. So from that video, we can have extract one more modality, that is the audio. So we can actually take all these modalities into consideration and we can fuse them together. And I think that would actually improve our models even better. But as for now, we do not have the data set.
Okay, and so last question, let's say you can add you have another modality. Do you think it will be like easy or complicated to add it in the workflow? And do you think the workflow, using workflow will help you to, quickly expand to new modalities?
Yeah, so as I said, so basically the task, the one job which we have is the late fusion. Let's consider late fusion. So this job is basically taking inputs as a CSV files. So similarly, if we just add one more job which will extract some information from these videos, we can easily just add just one more parameter to this job, which is the information from, let's say, videos. And actually, this is a very great thing about Pegasus because it's a DAG, and we can easily specify what are the inputs to the jobs and output to the jobs. So I don't think that will take much effort and can be done easily.